So it's a great pleasure for us today to have Florian Boßmann from Harbin Institute of Technology as our speaker. Just a few words about Florian. He started off his PhD at the University of Duisburg, Essen, where he also did his undergrad, and then moved with his advisor Gerland Plonker to the University of Göttingen, where he also obtained his PhD. And then after in that PhD, he was already working on the in the area of non-destructive testing, which he then continued as a postdoc as a project coordinator of a inter-university joint project. And I think during that postdoc time, he already started exploring the similarities between non-destructive testing and seismic imaging, which he now continues, and I think he will talk more about this today. After his postdoc in Göttingen, where he coordinated this project, he went on to Passau, also in Germany, where he did first a postdoc at the university and then also at the Applied Research Institute of the Fraunhofer Society. But now for a few years already, he has has worked as an associate professor at Harbin Institute of Technology in China, and especially has a strong association to geosciences there. And so we are to seismic imaging in particular. And so we are very interested in what he has to tell us about how we should move beyond SVD. So Florian, the floor is yours.
Yeah, thank you for this long introduction. It's quite interesting to hear from someone else what I already did. So I've called this talk Beyond SVD, 2 new adaptive models for moving objects. And we will see later on what I mean by moving objects. And as, can I click? Yeah. As Felix already said, so we're coming from the seismic data processing perspective here, and it's also close to ultrasonic data processing. But because I know not all of you are familiar with this one, I will also give a motivation based on video processing. I think that's a bit more easy to understand. And then I will tell you what goals we try to obtain with these models and what requirements we need. And then later on, go into both models in detail. So we have this shifted rank 1 approximation, that is one model. And this is the more simple model, but we first need to understand this one, and then can move on to the ORCA model, which is basically an extension of the shifted rank 1 approach. So let's look into the motivation. So imagine we have a video like this. So this is a video from the USF sports action data set. You can find it online. Let's see if this works. So you should see the video right now, I hope. So this is a very simple one. You have constant background and just one person running from the left to right. There are also like other persons in the background, but for this talk, it's not so important. We don't focus on these ones. Close this again. So this is a video. And now the idea is, can we divide this into backgrounds and the person? So basically we have, if we would describe this video, we can say it's contained out of, it's composed out of 2 objects. It's basically the background, and then there is this person. And what we could do is just apply SVD to it, so singular value decomposition. And what this will do, like the first or the largest singular value, singular vector pairs, you will find will give you the background. And this is because this background is something constant, and this is something that the SVD can easily catch. So it will reconstruct the background in the first pair of singular value, singular vectors. And then if you look at the second one, you will get this reconstruction. And it looks like it's trying to catch the person here, but because the person is moving, it is not able to really catch the person here, but somehow it's like blurry. It's a blurry combination of the start of where the person started and where the person ended, like this. So what we see is that like constant objects, like the background, is no problem for the SVD, but everything that is somehow moving in the video can make a problem. And this is where we are going with the model. So we are trying to incorporate this idea of moving objects into the SVD. So if we now go to seismic and ultrasonic data processing, so where we are coming from, we can see something similar. So first, maybe I explain how this works. So this is a setup found in ultrasonic testings. You have some emitter that sends out ultrasonic waves, and you have a receiver somewhere, and these red lines could be possible waves that you measure. So there is a direct wave that goes from emitter to receiver, and then there are other waves that are reflected either here at the defect or here at the bottom of whatever you're measuring. So maybe this gray part is part of a steel tube, then the inside surface of the steel tube would reflect the ultrasonic waves. And then you obtain data that looks like this. So one column of this matrix is basically what one receiver would record. But instead of only doing this measurement once, you do it several times and then put the columns that you recorded next to each other. And this is how you obtain this two-dimensional data. This is ultrasonic data. You can do the same with seismic data, but instead of ultrasonic wave, you have seismic waves. And instead of measuring a steel tube, you're just measuring like the earth layers inside the earth or something like this. But you already see these data, like they show similar structures. And now the question is, what is an object in this kind of data, and what does this moving we saw in the video refer to? So an object could be, for example, this complete wave we have here. This signal we are recording here is just the wave that directly travels from emitter to receiver. So it will be the first signal we receive, and it will also be the strongest one. And the object down here, this is the last thing we receive, and also mostly the weakless one. This is the one that is reflected by the back wall. So this is this last line we see here. And then in the middle, we might have some objects, some waves like this one here. And these are reflections from any defect inside the material. So we would call these waves, this ultrasonic wave would be the person in analogy to the video. And now if we look, for example, at the seismic data and at this wave that's going through here, we see that on the left side, it's a bit higher than on the right side. So that means here for these measurements, it was recorded earlier in time than for these ones. Here the measurement, here the signal comes in a bit later in time. So we can see, we can say for the measurements from left to right that the wave moves back and moves later in time. So we have some movement here from a early position in time to a late position in time. And another thing we see, like when you think of the person, when it's moving, the person is moving arms and legs. So the shape of the person is changing depending on what the person is doing right now. And we can see the same things happening for ultrasonic waves or seismic waves. For example, here, first, we have this reflection from the back wall. It looks like maybe two waves, and the first one is a bit, is not as strong as the second one. And then suddenly these waves merge together and form one string signal. So at this point, the back wall reflection we had before is changing its form and forms a new kind of signal. So these are the analogies between the video processing and the seismic data processing.
So there's a question here in the chat saying the outputs are still images, not videos in this. Could you maybe comment on this?
For the video processing data, the output is also videos. This image here is basically the left-hand side singular vector, and then combined with the right singular vector, we will get we will get a 3D tensor that would form the video. I just showed like one snippet of this video from the reconstruction here. And for the seismic data, it's normally we are working on these 2D images, but there's also, you could also think of scattered data or also of tensor data. But for this talk, it's all 2D images. Okay. Should I close this top section here somehow? I don't know if this is.
Top section?
Yeah, can you, I'm not sure if you can see it. Okay, it's fine. Okay, so now what's the idea of our models? So we saw that in different applications, we have these different kind of objects like seismic waves, ultrasonic waves, or this person, and we want to somehow catch their movement and their kind of transformation, if they're moving arms and legs, or if the seismic wave is changing somehow. And the idea behind this is that we want to give some physical objects like this seismic waves, we want to give it a mathematical form. Because if you look at many of the transforms that are used nowadays, like Shearlets, Wavelets, or also if you go to the PDE and apply a full waveform inversion or things like this, most of these transforms take the coefficients that we measured, so the data, and they transform them into another coefficient space. So for Shearlets, for example, you take an image that is just a union of pixels, basically, and you transform it into the Shearlet space, where it's again a number of coefficients. But if you want to find out if this picture contains like a car or a person or something like this, you still need to analyze the Shearlets, because these coefficients like don't really tell you something about complex objects in the real world. So this is what we want to address with our models. And there are some transforms that do similar, that do things like this. So we already saw that the SVD, if we have a video with constant background, then the singular value decomposition is perfect to catch the constant background. So this transform is already doing something like this. But we saw like if there's an object moving, then this transform fails. You could also say that like machine learning, if you train a classifier, like you input an image and the classifier tells you this is a dog or this is a cat or something like this. It's also kind of this transform that transforms your coefficient space of images into an object space by just telling you what's inside the image. But the problem with machine learning is it requires a lot of data, and there are some applications, especially in seismic data processing, where this amount of data simply is not given. So we cannot rely on machine learning techniques here. So the models that we design, as I said, like they are supposed to present real world objects into a mathematical form. So we have, on the one side, we have the requirements from the real world that we want to fit the model to an object. On the other hand, we have the mathematical requirements. We still need to be able to handle this one. And for this talk, I would say we stick to like 3 requirements from each part. And for the real world requirements, what we want the model to capture is first some kind of the global form. So for the seismic data, for example, this would be some seismic impulse that forms the wave. Then the second one is we want to track the movement with our model. So there should be some parameter that tells us this seismic wave is at this and that position right now. And the third thing we want to capture is the change of the wave. So something that tells us if you remember the reflection from the back wall, something that tells us right now there was happening a change in the back wall and the signal is changing from these 2 waves to a combined impulse. So this is the application, the requirements from the real world. And on the other side, we have the mathematical requirements. So first of all, we want to have something sparse. So we want that our data is sparse in this object space. And this is not really a hard requirement because most of the time it's already given by the application. So for seismic data processing, most of the time you're not interested in the complete data. There are only like maybe 5 or 6 important seismic signals in the data that you're really interested in, that show you some really important things. And the rest is maybe noise or some smaller waves that are not of that much interest. So the sparsity is something that is easy to achieve if you're going to this object domain. But the other two things are quite hard because the model can't be too complex, because you still want to be able to handle it algorithmically. So you still want to be able to solve the approximation problem in the object space. And the third thing we want is we want to have some theoretical results. We want to handle the model theoretically. And so these two requirements are, you need to balance basically between these two requirements and the requirements from real world. The more detailed your object becomes, the more hard it becomes to handle it mathematically, and vice versa. So saying this, we can go into the first model. This is a shifted rank 1 approximation. And this is basically a direct adaptation of this, of the SVD we've seen before, combined with a shift operator that I will introduce first, and then it's quite clear where this model goes. So this is like the more simple model of those two. So the idea is, we already saw SVD can already detect everything that is like constant in position, that doesn't move. And maybe we can just upgrade the SVD to include movement, and we will do this with a column shift operator. And the column shift operator, we define it like this. So first it goes from the matrix space back into the matrix space, and it takes any matrix A, and then the first column. So I'm using MATLAB notation here. So this column 1 means this is the first column of A, this is second column of A, and so on. And the first column is multiplied by a matrix J to the power of lambda 1. The second column by J to the power of lambda 2, and so on and so on. And this matrix J is just a shift matrix. So if you see this here, if you multiply the column vector with this matrix, it will just shift everything by 1 pixel down. So what this does here is just shift the first column by lambda 1 pixels down, the second one by lambda 2 pixels down, and so on and so on. So in lambda here is just an integer vector of length, n is like the number of columns we have. So, and there are some nice properties of this operator that we will need later on. First of all, it's linear. This is easy to see. You can just plug it in. Then the inverse is, of course, just taking the negative shift. The Frobenius norm under this operator stays constant, so that's also quite nice. And we know that shift in time domain is equivalent to phase multiplication by phase in Fourier domain. So we can write this operator also in Fourier domain as pointwise multiplication. So this is here the Hadamard product, the coefficient-wise product of this vector by a Fourier domain. And F here, F is the Fourier transform. So having the shift vector, let's go back to the SVD. So the SVD writes the data D as this matrix product, U as matrix U times matrix S times matrix V. Here's a transpose conjugate complex missing. And this S is just a diagonal matrix with the singular values on the diagonal. So we can write this as sum of these rank 1 matrices. So this is just the pairs of singular vectors and singular values. And we already saw that one of these pairs, like the first pair, is perfect to represent the background. So we would call this one here an object. So we could say that the singular value decomposition writes the data D as sum of n objects. And D is object sparse if and only if D is low rank. That's what directly follows from this. Now, how can we teach these objects basically to move? Well, instead of taking only a rank 1 matrix here, we can take a shifted rank 1 matrix. So we basically, you see there's still a rank 1 matrix inside, but now we are allowed to apply a shift operator to this one. And now we say that the data D is object L sparse if it can be written as sum of L of these shifted rank 1 matrices. So this is, if you compare like this formula here and this one, it's quite similar, except that we have the shift operator that can be applied to each rank 1 matrix here. So this is basically the upgrade of the model. Now, to give some visual like motivation for this one, we're going back to the seismic and ultrasonic data, and assume you have a seismic or ultrasonic wave. So this is just some oscillating signal. You see it's like strong in the middle, and then it goes to 0 on the top and bottom. So this would be a seismic impulse or an ultrasonic impulse. And now, depending on where this impulse is traveling, it's getting like stronger or weaker. So it has some kind of amplitude, and this amplitude we can write also as a row vector, and you see it's strong in the middle. So that means that when you're standing here at this position in the middle, you are close to the source of the seismic wave. And if you're going to the left or right, you're more far away from the source. So the amplitude is decreasing. Now, if we combine these ones to a rank 1 matrix, we get this one. And now the important thing is if we apply a shift. So here, for example, I've chosen a shift lambda that looks like a parabola. Then we get some matrix that looks like this. And this is a shifted rank 1 matrix. And if we have a look at our ultrasonic data or seismic data, these are two more examples, then we see that the forms that appear here, like also these parabola-like structures here, or also here, this wave moving down, it looks very, very close to what we have here. So it seems that like this simple adaptation is already quite fitting to the data.
But
now,
but you said, yeah? Sorry to interrupt. You said you just applied the shift that is a parabola. So if you don't know the shift, it's not clear. At least, I mean, for the SVD, there's an algorithm how to do this. And here, if you know the shift, you can sort of make this decomposition. But if it's an unknown shift, that's not a priori obvious how to make this decomposition, right?
We are recovering the shift during the decomposition. This was just like example, like an example to show like that this forms appear here. But we will see like on the next slide, so we recover it. Yeah. So that's basically the problem. Like we have given our data D now, and now we want to find the closest shifted rank 1 matrix that fits our data. So this is basically the approximation problem that you were asking for. We are solving for one shifted rank 1 matrix at a time, and then apply the same algorithm to the residual and so on. So basically, iteratively solve this problem multiple times. And so now we need to find lambda, u, and v for this one. And we can use the properties of the shift operator to push it to the other side. And then we already see, so we have some shifted data here and just a rank 1 matrix here. And the rank 1 matrix, we know it's the SVD. Like we just need to choose the largest singular value, singular vector pair to make this approximation. So we don't really need to worry about how to find u and v. We only need to worry about how to find lambda. Now, the rank 1, the error of the rank 1 approximation is basically the Frobenius norm of this one minus the largest singular value. So we can rewrite this minimization as this one. And then we note that the shift itself doesn't change the Frobenius norm. So this first term here is constant. So instead of minimizing all this, we can just maximize the second term here. And then we rewrite this a bit by saying this is the largest singular vector, singular value. And we can also write it as maximization over lambda and the vector u. And we take the matrix vector product here with a row vector from the left side. Here's a norm 1 missing. The vector u should be like normalized. And the trick now here is that we can split this problem. Like we optimize over lambda, we fix u, optimize over lambda, and then we fix lambda and optimize over u, and we do this iteratively until we converge to some point. And both problems on its own, like if you fix lambda and optimize over u, then this is just the largest singular vector that we're looking for. So this is easy to solve. if we fix U and optimize over lambda, like if you write this down and go to the details, this also just a linear problem you need to solve, and it's no longer hard because you can separate the different parameters that are in lambda. So this is quite easy. So this would be how we were are able to reconstruct lambda. And now I cheated a bit here by this writing, because this is equality here, but only if you maximize over lambda and U at the same time. What we're doing here is fixing lambda and then optimizing over U, and then the other way around. So this algorithm is does not necessarily converge against the optimal solution of this one, but may get stuck in some saddle points or something like this. So the question is, how good is this algorithm to approximate our problem? And we could show the following things. First, we only need a finite number of steps. It will always end after a finite number of iterations. That's the first thing. The second thing is that the norm we try to maximize also strictly increases in each iteration. So at least we are producing like a growing series of values here. And the next thing we could show is that we are also finding a global optimum, a local optimum. Local in the sense of U and lambda. So if you have a slightly different U and any other lambda, then this value, the new value you will produce, will be not or at most as good as the value you already have after the convergence of our technique. So we have some theoretical control over this algorithm here. We know it's converging after a finite number of steps, and we know it goes into a local optimal point. Okay, this one is not so important for this talk here. Let's have a look at some examples. So the first thing we did is we took this seismic image here, and we added some noise. Like the noise is getting stronger and stronger if you go from left to right. And now the question is, can we still find at least like the largest seismic wave here on the top? Can we still find it? And the way we've tested it is we took this noisy image, applied the shifted rank 1 approximation to it, and then the red plots that you see here, this is basically the parameter lambda. This is the position of the seismic wave that the algorithm is predicting. So if this position coincides with the seismic wave, then we know that the algorithm is doing fine. So, and we see that even for the higher noise, most of the dots are really following the seismic wave, so it's doing fine. But because of the noise, we have those random jumps, and this is one thing that is not fixed in this model right now. This model is just looking for any shift vector lambda. So this means that it can arbitrarily shift, but like normally you would say if you track some signal on top of here, in the next measurement, it can't jump completely down to here. So this is something that is physically impossible, but not introduced in the model right now. And we will fix it with the second model I will show you later on. So the next thing from video processing, the same question we had before. We have this video that you have seen. If we apply 2 iterations of our shifted rank 1 model, can we find the background in the first iteration and the person in the second one? And what you see here is like the one frame from the first reconstruction and one frame from the second reconstruction. And it really looks like we're finding the background and we are finding the person. So it all looks fine. But if we look at the video now, so the video I'm showing you now is the reconstructed background and the reconstructed person combined. Oh. Here. And this is what we are saying. And you see, like, the background looks fine, the person looks fine. I made the background a bit less strong here. That's why it looks so white, just to more emphasize on the reconstructed person. And it also walks from left to right, but it's not moving any legs or something like this. So there seems to be trouble with this one. And this is because the shifted rank 1 model, it introduces the shift vector, which allows the object to move, but it doesn't allow the object to change in form. So it can't like move any legs or arms or something like this. It can just move the position of the object. And these are the two things that the shifted rank 1 approximation cannot do. And this is what we try to fix with the next one, with the ORCA approach. So ORCA stands for object reconstruction using K approximation. And like K approximation, we will see now what this means. So if we go back to the shifted rank 1 approach, our object model looks like this: rank 1 matrix plus this shift operator. And the problem was, first, the shift operator can be arbitrary. So it means that the object can suddenly teleport from one position to another, what is completely unreasonable, but not protected by the model. And the second thing is, like, what we've seen, that the person can't move arms and legs. Like, the only thing that can change from measurement to measurement is hidden in this V. It's basically, in the video, it would be the brightness or the illumination of the person. Or if you remember the example with the ultrasonic or seismic wave, we can change the amplitude, but we cannot change the form of the wave. So we cannot change maybe the frequency or the oscillation. We could only change the amplitude. So what we really need, so if we want to fix this, the problem, especially for changing the form, if we want to change the form of the object, make the person able to move arms and legs, we have to go away from these rank 1 matrices here, and we have to use a complete matrix. So our new model is a complete, not low rank matrix, and then shift operator applied. But we want to have two restrictions, and the first one is the shift now must be smooth. We will see on the next slide what this really means. This is a restriction, so we prevent these teleporting or jumping effects here. And the first one is, the second one is, the columns of view should be similar. That means like two neighboring columns here should be similar. That means you can change the form of the object, but you shouldn't change it too much. So we don't want, like in a video, a person randomly changing into a car and then into a tree or something like this. It would be like a big change, but we just want to allow some change, but not too much. Now that's the question now. We have these two restrictions. How do we include them in the model? Let's first talk about the restriction to the movement, so to the vector lambda here. And this is quite an easy one, because normally this is restricted by some physics or some other things you already know. Like for this seismic waves, for example, we know how fast they can move through the Earth. It depends a bit on the material, but you have at least an upper bound. What's the fastest speed you can expect? Also for the person running in the video, you could maybe expect that it's like maybe at most 15 kilometers per hour or something like this. You have a reasonable upper bound that you can find. And we can just enforce this by using inequality constraint, because we know if this upper bound is broken, then there should be something wrong with the data or something wrong with our assumption about the physics that's underlying. So this will just be an inequality constraint. Then the next one is a bit more complicated. What do we know about the change of form or appearance of this matrix U? The problem is can be here, that this can be arbitrarily large. So imagine the video, you also have like a tree in front, like somewhere in the front of the image or in front of the video. And now the person is running from left to right. And at some point it's running behind the tree. That means that within a few frames, the person will go from perfectly visible to completely hidden behind the tree. And then in the next few frames, it will go from hidden behind the tree to perfectly visible again. So that's quite a very large change of the object we are allowing here. So we can't just limit the change of the object in each column. But what we can assume is that these things are not happening too often, and that most of the times this object, whatever we are tracking, is well behaved, and this effect is only like occurring very few times in the picture. So instead of using some inequality constraints here or so, this is perfect for a regularization term. And if we include this in our model, we would end up with this minimization problem. Here, I only show it for equidistant sampling. Like you can do the same for non-equidistant sampling, but it gets just the formula is much more complicated. There's not much magic behind it. And the first term we see is then the data fidelity term. So we, of course, try to fit our model to the data. I already moved this shift operator from our the matrix U to the matrix D. That can just be done because it's linear and not changing the Frobenius norm and things like this. So it's quite easy. Then we have this penalty term here. So we have a parameter mu that weights the penalty term. And then we're just looking at neighboring columns. So this is the case column of our matrix U, and this is the next column, the k+1 column. And we're calculating the difference and then just taking the 2 norm of this one. And we sum this up over all neighboring columns. So this is what we would call the total change of the object. And this is what we want to penalize when it gets too high. So we have some parameter mu to control it. And then we also have the inequalities coming here from our movement lambda. We want to say that the difference between two positions, so lambda k is the position in the case measurement, and lambda k+1 is the next position. And this, the difference between them should be smaller or equal than some constant c. So we say this is Lipschitz continuous because we have equidistant equidistant sampling. So normally you would also have like the distance between both sample points on this side, but because it's equidistant, we can just skip this one. So this would be our model. And now again, we have set up the minimization problem, the model. The next question is it too complicated, or can we actually solve it? And to solve this one, the first thing we do is we consider that lambda is fixed, or we already know it. And we have a look at this model now. And what we realize is we have the Frobenius norm of some matrices here, and we have the 2 norm of some vector here. And this is perfectly fine, a quadratic minimization problem that we can actually solve. So we do this by rewriting it so in the terms of the rows of our unknown u. So you see here, this term is in terms of the columns, and now we switch to the terms of the rows because then it becomes more obvious how the minimization problem looks like. And you end up with this kind of minimization problem, an identity matrix here in the quadratic term. This comes from the data fidelity term. Then we have a linear term here. This also comes from the data fidelity term. There would be a constant term also. We skip about this one because we're just talking about the minimization. We don't care about the constant terms. And then from this penalty term here, we get this matrix mu times t here, and t is just a second order difference matrix. So if you write this down and look at the formulations, if you look at the rows, you will just get exactly this matrix. So this is the minimization problems we get. Now, the next thing to realize is that this inner term here is just a minimization problem of the jth row of our matrix U, and all the summands are independent. So instead of minimizing the sum, we can just minimize each of the coefficients on its each of these terms on its own. And if you do this, like you take the derivative set to 0 and see where the minimum actually is and things like this, you see that the minimum will be obtained at the minimal value that will be obtained is this value. So we have the inverse of the system matrix here. And this is actually like well behaved. We can show that this is a positive definite matrix, so everything is fine. So we can just take the inverse system matrix here, and then the inner product, Frobenius inner product with this term. And now that we know that this is the minimal value of one of these terms, we can get the overall minimal value by just summing them all up. And what happens is you get, again, Frobenius inner product with the inverse system matrix. And here you get basically the correlation matrix of our data. And the idea is now, first we thought lambda is fixed and we get the minimal value of this one. So to find lambda, we can just try to minimize this term over lambda. And if we succeed with this one, then we know this is our optimal shift, and we can just plug in the shift we found in here and then just solve the quadratic problem. So again, finding the matrix U is no problem. The problem is, how can we find the lambda? And of course, like, instead of minimizing this one, we will just maximize the positive term, then we can skip the minus here in the beginning. So how do we maximize this term? And there is where the K approximation comes in. So this is a term from the last page again, that we want to maximize over lambda. Now we can rewrite the Frobenius inner product just as sum of these terms. This is just the Frobenius inner product rewritten. And then we can move this shift operator to the other side. This, again, if you look at the shift operator, because it's linear and well behaved and everything, this works perfectly fine. So we don't get a shift here, but we get a shift in the difference on this side. So this is basically the term we want to minimize. The problem is, so we know these coefficients from the inverse system matrix, these are fine, but here we have this lambda j minus lambda k, and we know it's integer solution, so it's kind of a combinatorial problem, and there are a lot of values that could happen here, and this problem seems to be NP-hard. I'm writing here seems to be NP-hard because we didn't prove it, but we found so many relations to other NP-hard problems that we think it's like unfeasible to try to solve this problem. But one thing we can do is we can make use of the Lipschitz continuity of lambda that we used before to simplify this one. And we do this in the following way. We define the K approximation now. This K approximation, tau K of lambda, is just the same sum. Like you see, it's the same sum as on top of here, but we have the restriction that J minus K must be smaller or equal to K. Now, you can think of this is like the sum of matrix entries. So you have like an n times n matrix and you sum up all the entries. And then this is the same sum, but we take the band limited version of the matrix. So we cut off after some diagonals. And why does this help us? Well, consider again these differences here. We have lambda j minus lambda k. Let's say we have lambda j minus lambda j plus 1. And we know it's Lipschitz continuous, so we know that lambda j minus lambda j plus 1 must be somewhere between minus c and plus c. The same if we have lambda j minus lambda j plus 2, it must be somewhere between minus 2c and plus 2c, and so on. So by restricting ourselves to only a band, the number of possibilities that can come up here are much less than for the complete problem here. So we hope to choose K, to be able to choose K so low that actually the number of possibilities is low enough that we can just brute force the problem. That's the approach behind it, basically. We will see later on how to exactly solve this one, but this is the idea behind it. Now, the question is, again, we have an approximation, this K approximation of some term that we actually want to maximize. And the question is, how good is this approximation? So if this term here is completely different to that actual term that we are considering, then there is then it doesn't make sense to solve the approximation problem. So for this, we could show the following. So lambda k max, this is the best vector you can find if you maximize the K approximation. Now, what is the global optimum that we would like to find? The global optimum is just taking the n-1 approximation and taking the path from the plugging in the paths of the n-1 approximation. So if I go back, if you set for k n-1 here, then you see that this is actually not a restriction, but this term and the upper one will be exactly the same. So writing n-1 here is just a more fancy way to say like we are solving the exact same problem, the exact problem. But what we actually could do is we could solve the k approximation to get the path. So we get the path from the k approximation and plug this into the original problem. So this is what we can solve, and this is what we could solve. And we can show that the difference between those two, so the second one is always worse than the first one, we know this one, but the difference is bounded by this term. And we have here some constant that is not too important. It's somewhere between 0 and 1 over n, so it's not so large. Then we have some quadratic term here, and some exponential decay here. So this parameter that is appearing here depends on our regularization, and basically said the higher you choose your regularization, the worse the approximation will be. Like this, this exponential function here will decrease less and less fast the higher the approximation is. So I'm not going into too much detail into the proof, maybe just where these two terms are coming from. So there is a nice publication by you. You can have a look at it, and then you will see that the inverse system matrix has an analytic form that can be written like this. And there are the cosinus hyperbolicus functions that are basically exponential functions. And it shows that these ones are decreasing if you go away from the diagonal. And this is where exactly this exponentially decreasing factor comes from. And then if you look at the difference between the original problem and the k approximation, then you get the exact same sum as before, but now you have j minus k must be greater than k, capital K. And so you get this sum, and the number of summons here is exactly in this order. So you have like n minus k squared summons basically. So this is where these two parts are coming from. So you have some quadratic decay and some exponential decay in the approximation. Okay, this is not so important. So we have the k approximation, and we know that it is a good approximation of the original problem. Now the question is how to solve it. And this is actually the minimization problem we want to solve. So again, this is the term of the k approximation inside. And now we just want to maximize it over lambda, and lambda should be Lipschitz smooth. We rewrite this term, so we split up the sum. The first one goes from 1 to n. And the second one, we go k equals j minus k minus capital K. And it should go to j plus capital K, but we're only going to j minus 1 because this term is symmetric, so we can skip the upper half basically. And for j equals k, this term is constant, so we can also skip this one. And then everything that's the inside sum here, we call it w prime, and it depends on some parameters j and all the differences that appear here in the second term. And now we want to rewrite w prime a bit in the following way. We define rj. Rj is just the difference between two positions. And that means we already know that minus c and rj, that rj is between minus c and c. And also we know that any difference between two positions can be written as sum of these rj's by just summing them up. But this means instead of using this w prime that depends on j and all the difference, we can just write it as some w that depends on j and all the appearing rj's, which is basically the same. So now we are no longer like really interested what's behind this. Like you can forget about this formula. It's just some value that we are able to calculate. And with this in mind, we can rewrite the chi approximation as this minimization. So again, as this maximization. Again, we want to maximize now not over lambda, but over rj, and they are between minus c and c. We have the sum from j j from 1 to n again. And then inside, we just have these weights that we can calculate beforehand. And this is again a combinatorial problem, but we can solve it by constructing the following graph. And this is a bit more complicated, so hope you stick with me. So first we put the node 1 in the beginning and the node n+1 in the end. And then for all our columns, we put one partition of the graph. So here's a partition that belongs to the j's column of our data. Here's a partition that belongs to the j's-1 column of the data. And each node has 2 entries. The first one is just the partition it belongs to. So this node belongs to partition j. And then there is, I would call it the memory of the node. This the values rj to rj minus k plus 2. So there are k minus 1 entries in there. And this is kind of the memory. It's like how far this node can look back to the other columns. And now we connect 2 nodes of the partition j minus 1 and j only if the memory is the same. So we have a coefficient, we have the coefficient rj minus 1 here in the memory, and we also have it here. They need to coincide. The same for rj minus 2 and so on. So we only connect them if the memory coincides, and the weight of the edge is exactly the weight that appears in the sum here. And if we construct the graph this way, we get n+1 partite graph. So we have like n+1 partitions. Each partition has 2c plus 1 over k minus 1 nodes. So we see here we have an exponential growth of the graph, but only in the current parameter k that we can control. So that was what we were hoping for. And the nice thing is, if you have the longest path from a to n+1, so you sum up the weights, and the one with the largest weight, the longest path exactly solves this problem. Because if you take any path that starts as 1 and ends at n+1, this means the path goes to each partition and basically chooses some parameters rj and sums up the weights that belong to it. And in the end, you have this sum here. So we need to solve the longest path problem on this graph. And the nice thing is it's a direct acyclic graph, and it can be done in linear time. So this is basically what the ORCA algorithm is doing. So we get the data, we construct this graph, then we solve the longest path problem. We get the path vector lambda from this one, and then we go back to the quadratic problem. We remember once the vector lambda is given, calculating u is no problem at all. So the complexity of this algorithm is n times 2c plus 1 over k. So we have some exponential part here, but something that we can control and that doesn't depend on the data. And then the second part is less important here because this normally has a very small constant. So we only need to concentrate on this part here. So let's have a look at the results for this algorithm. So first of all, what we did, we measured the runtime. So we have 2 implementations, the parallel one and the non-parallel. The blue line is the parallel one. You see it's a bit more overhead, but it's faster for large K. And the green line here is O of 2c plus 1 to the power of k. That's exactly the runtime behavior that we would expect, because that's the number of edges we have to check per partition. And we see that both implementations exactly fit this runtime. And the next thing, we checked how the runtime behaves if we increase the data. So we've seen before, like, this is the important part, and we would only expect a linear increase in the data. Maybe slightly more than linear if this term also comes into play, but normally, as I said, there is like a quite small constant in front of it. And we see this runtime here is basically linear, so exactly what we would expect. We see some peaks here every now and then, but if you look closer in it, it's just the implementation in MATLAB using the fast Fourier transform, because the fast Fourier transform only works well if you have small prime factors in the data, because otherwise you can't divide the Fourier transform into smaller ones. So this one shows the largest prime factor of n, And as you can see, the peaks here exactly coincide with the peaks there. So that's nothing too much to worry about. You could just extend the data to maybe a factor to some 2 exponential, and then you're fine. The next thing we wanted to check was the approximation rate. And this is a bit more complicated because for the approximation rate, we would need to know the exact optimum. And for that, if we would know that, then there would be no need to approximate it. So instead, we did the following 2 experiments. The first one, we construct this diagonal matrix with ones on the diagonal, but there's always a gap in between, and the gap is getting larger and larger. And what we would expect the algorithm to do is, if we apply ORCA with some value k on this one, then it should find the optimal shift. But at some point, the algorithm will break because the gap gets too large. Remember, I said in the graph has a memory and can look k-1 nodes back. And we would expect if this gap gets larger than this k-1, then the algorithm gets lost. And this is exactly also what is shown here in the graph. So all these lines are the reconstructed path. The blue one for k equals 3, then the next one 4, the next one for k equals 5, and so on. And we see the optimal shift would be just a straight line going up. And we see that all these algorithms start with a straight line going up, but at some point they break when the gap is getting too large. And only for k equals 15, that's the largest gap we included here, we can reconstruct the original, the perfect shift. Then the next thing we did, we calculated the approximation error for some random matrices, but only with 16 columns, because with 16 columns, then we're still able to also calculate the exact solution. And we plotted this one for different values mu. What we see here is also exactly what we expect earlier. I told you this exponential factor in the error approximation is getting worse, or like the decrease gets less for large mu, and it's exactly what you see here. So for mu infinity, you have the worst approximation error, and then if you decrease mu, it's getting better and better. So this means the higher your regularization parameter is, the higher you should choose k. Now we're doing the same 2 experiments again from the beginning that we did with the shifted rank 1 approximation. We take noise data, we apply the ORCA algorithm, we plot the path, and if the path fits the seismic wave, then we know that it found the correct signal. And we see here, it's oscillating a bit because of the noise, but it found the wave quite nicely. And the interesting thing is here, this noise is so high, we have a PSNR value of 0. And you can only see the seismic wave in the background if you really zoom in into the data and know where to look for. But still, the algorithm is able to track the movement here, basically. We also compared it to Shearlet denoising. So we used our ORCA method for denoising and compared it to Shearlet denoising, which is very good for seismic data because this Shearlet structure fits seismic data quite well. And we see, like on low to mid-level noise, we are not doing as good as Shearlets, but then on mid-level, we are maybe the same level as Shearlets. And then for the high-level noise, the same we see here, we're having a better approximation error, or a better PSNR for the reconstruction than Shearlets. So the other example we had was the video, where we are trying to track the person that is walking through the video. And we did the same here with ORCA, two iterations. First, we found the background, and second, we found the running person. That's no surprise. But now the question is if the person is really moving. And if we look at the video, we see now that we really have some leg movements. Every time when the legs are crossing, maybe you can see it, there is some blurring effects. So there is still some minor troubles, but altogether, it's working much, much better, and we can also track the movement now. There are I would say two limits of the method right now. The first one is, if you remember the ultrasonic data where there was a defect here on top, we were now using this method, or again, 2 iterations to separate the signal of the surface and the back wall from the defect, and it works quite fine. But you can see this defect here is somehow fading out into the data, and this is for some reason we will see on the later slides. So this is some effect that we would like to get rid of, but this is right now in the model. So the second one is we now tried it to use this method on another video, on this one. So this is quite more complicated because there's much more going on. There's like much more movement. Also, the camera is moving, and also the video is much faster. Like especially the ball here is much faster than the running person in the other video. So we applied 3 iterations of our method. The first one, we get this one is like a kind of a generic background. You can see the players a bit, but not too much, and the timestamp again. The second one is interesting. This one is the advertisement and the pattern of the grass. And if you think of it, these are the things, if the camera is moving, then these things are also exactly moving. So they are moving exactly with the same speed as the camera is moving. And the next thing seems to catch most of the players. And if we look at the video again, you can see that many of the players, they are moving in the same direction, and they are moving at the same speed. And this, for our algorithm at the moment, is telling our algorithm they're moving in the same direction, they're moving at the same speed, so they must be the same object. So it tries to capture all of them in the same object. And I said the video is quite fast, and this was also the problem here. So we needed to assume that like one player from frame to frame maybe moves like 12 pixels. This is already quite low. I think it should be even higher. But this means we have a complexity, remember, of 2c+1, so that's 25. Now, because this is 2D data, we have to square this. So this is 625, and then to the power of k, so 624 to the power of k, we get something like 244 million edges. So quite high. It still runs on a normal computer, but you see if you choose chi even higher, we're getting more and more into trouble. Okay, some summary and some outlook, where I will also tell you what's the limit of this method and why this happened, what we've seen before. So first, we had these 2 models, and based on mixed optimization. So we always had this mixed integer optimization. If we remember in the beginning of the talk, I said we have this mathematical requirements that we want to handle the objects. We want some theoretical results and also some algorithms. For both methods, it works quite perfectly. We also had the requirements for applications, where we say they should fit the applications. We also seen in the numerical examples that fit. But we think for the future, what these models show is that if you include a priori information or information about the objects you want to find into your model, then the results are quite promising, and it could work much better. But we think that at this point, we should take those models and really put much more details and more a priori information into this model, but then also stick to some very specialized applications. So the model at this stage are more like general for more applications and should be used as a blueprint, saying, okay, now I'm really going to seismic data, offshore data for gas reservoirs. So I can put much more information into the model and solve this special problem based on the ideas presented here. So there are some ideas how to extend this model. I'm not going into details, but maybe 2 things that we saw before. So I said for the ultrasonic example, this defect was fading out into the rest of the measurements. And we think this is because in our model, we are using the 2 norm here, the 2 norm squared. And the 2 norm normally encourages like smooth behavior of the reconstruction. What would be better maybe would be using a 1 norm in the minimization problem. But then we have the problem that this here is no longer a nice quadratic minimization problem. So this could be something interesting for future work, maybe to fix this problem. The other thing is we have seen that like all the football players were put into the same object because they're moving with the same speed. Well, we could say maybe we should limit U to be compactly supported so that it can only grab one player at a time. So this could be something for future adjustment. But again, then you really need to focus on the application and really know what kind of compactly supported data you want to have depending on the application. Okay, so here are the two publications. The first one is the shifted reg 1 approach from 2020. The second one you can just find on arXiv. So it was uploaded yesterday, should be available by now. It's in submission, but if you're interested, this is the first version on arXiv. Thank you very much.
Yes, thanks a lot for this presentation.